Okay, so today's third instalment of statistical tests in biology is something called the Spearman rank correlation test. And this is to see if there is a correlation between two sets of paired data. Okay, so if you go up a tree, does the leaf size increase? And there's a couple more examples on this page here. Okay, so light and leaf length. So if you measure light intensity, does that increase or decrease the leaf length? Is the amount of oxygen associated with an increase and decrease in organisms. So this is the equation that is used. So we're trying to calculate this value here. This is the Spearman's rank correlation coefficient. And it is equal to, it says here, 1 minus 6 times the sum of the differences squared, I'll come back to that later, divided by the number of pairs multiplied by the number of pairs squared minus 1. And again, in an exam, you will be given this equation. You won't have to remember this equation. This equation will be provided for you. So the easiest way to do this is just to have a look at an example. So we have some data here. So this data, we've got dragonfly larva density. Okay, and then we've got tadpole density. So the dragonfly larvae prey on the tadpoles. So is there a correlation between the number of dragonfly larvae and the tadpole density? Okay, so as we've done with all these others, the first thing we do is to construct a null hypothesis. So in this case, our null hypothesis is that there is no correlation between the density of tadpoles and the dragonfly larvae. Now, the important thing about the Spearman's rank correlation coefficient calculations is that we have pairs of data and we must keep those pairs of data together at all times. Okay, we don't rearrange the pairs of data. The pairs of data must stay together at all times. So, the first thing we do is we rank the data set 1. So we rank the data from the lowest to the highest. So you can see here, here's my dragonfly density. Okay, so we've got 1s, 2s, 3s, 5s. Okay, now if there are two the same, what we have to do is we have to work out a sort of an equidistant rank. So these two are in positions essentially 1 and 2. So if we add 1 and 2 together, we get 3. So we divide that by 2, and that gives these to a rank of 1.5. Okay, so our next lowest number is this number here, 2. So that's our rank 3. Our dragonfly density of 3 goes into rank 4. And then we've got 2, so 2 5s here, that are going to take up the rank essentially of 5 and 6. No, sorry, 6 and 7, sorry. So if we add those two together and divide those by 2, we get 6.5. So we've ranked them. So we've got here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 sets of data. So our highest rank should also be 12. You should never have a rank higher than your number of pairs of data. If you've got that, you've gone wrong somewhere. So we've ranked our data. Now, the second thing is, third step, we keep our pairs of data the same. This is really important. And then we rank our data set 2. So we've still got our pairs of data, so 3 and 86, 6 and 46, but we're now going to rank this data set here. So 15 is our lowest, so that gets a rank of 1. 30 is our next, so that gets a rank of 2, and so on. So we rank data set 2. So far, so good. The next thing we have to do is we have to work out the differences between the rankings. This is what we're looking at. So we take rank 1 away. Sorry, we take rank 1 and we take rank 2 away from rank 1. So it's rank 1 minus rank 2. So minus 7, 3, 3.5, etc., etc., etc. Okay, so that comes out quite straightforward. That's quite easy. Now you can see we have a lot of negative numbers here, but that's fine because as with all good statistical tests, to turn our negatives into positives, we square them. So now we have the squares of our differences in rank. These were our differences in rank. Okay, so we squared them, and now we've added them all together. All right, and that gives us 129 down here at the bottom. And then it's just a case of feeding all this data into the equation. Remember earlier I added these up, and we have got 12 sets of data here. So 12 is our value of n. So our sum of our differences squares is 129, and our numbers of pairs of data is 12. So we've got 6 times 129. That 129, remember, is the sum of our d squares. Divide that by 12 times 12 squared minus 1. So that is 774 divided by 12 times 144 minus 1. You can see all the calculations here. Okay, so we end up with a value. So remember, we have to get away from 1, because it's 1 minus this value, of 0.549. Okay, that is our Spearman's rank correlation coefficient. Now, what we then have to do is have to look it up in a table. Again, another statistical table. You will either be given this data or given the table to look it up in. So we're going to look at the sign, we're going to test it for significance, and then we'll accept or reject our null hypothesis. Now, the sign is important. I will come back to the sign a little bit later. So we go to our table now. Slightly different. Looking up our degrees of freedom, we don't do n minus 1 for a Spearman's rank correlation coefficient. We do n. So we had 12 sets of data. So our significant value at the 5% level of confidence is 0.5874. So our value is lower than the significant value. So we are going to accept our null hypothesis. There is no significant correlation between the number of dragonfly larvae and the number of tadpoles. Okay, they're not related to each other. They're very closely, but it's not significant at the 5% confidence level, which is what we always look at. Okay, so it's very important that we always check our degree of freedom is the number of pairs. It's lower than that, so we're going to accept our null hypothesis. Now, I talked earlier about the sign of this. Sometimes it might come out to be negative. If it comes out to be negative, and if it comes out to be negative and it is greater than our significant value, there is a correlation, but it's a negative correlation. As one gets bigger, another one gets smaller. Right, I'm now going to show you another example of how to calculate the Spearman's rank correlation coefficient. Okay, so for this example, this is an exam question. So we've got the photograph below shows limpets, Patella vulgata, living on a rocky seashore. Limpets are snail-like animals with a conical shell. The limpets live on part of the shore which is covered by the sea twice a day. They feed on algae when the rocks are covered with seawater. When they are uncovered at low tide, they clamp against the rock to prevent desiccation. So a student investigated the relationship between the size of the limpet and their locations on the shore. A 40-metre transect was used, beginning at the low water mark and extending up a sloping rocky shore. At 1 metre, a 1 metre squared quadrat was placed every 5 metres on this transect, and the diameter of 10 randomly selected limpets was measured. The table below shows data collected from this investigation. So we've got distance from the low water mark here. We've got rank of distance. They've already done this bit for us, so they've ranked the distances. That was quite easy. We've then got the mean diameter of the limpets, okay, rank of diameters, differences in the two ranks, and the differences squared. Okay, so the first thing it's asking us to do is to complete the table on the previous page to show the missing data. Well, this is not going to be particularly complicated. Okay, so they've already ranked, so they're ranking from high to low, doesn't really matter. 1, 2, 3, 4, 5, 6. So we've got, they've then put in 8, so we've got 2 missing data sets. So after 17.4, is going to come 17.2. Okay, so that's going to be rank 7, and then this one will be rank 9. Okay, so difference in the two ranks. So we've got, so just let's double check what they've done. They've done this rank minus this rank, so we'll do the same. So 3 minus 9 is minus 6, and minus 6 squared is 36. 1 minus 7, weirdly, is also minus 6, and minus 6 squared is 36. Now, if you add all these together, you come up with an answer of 216. I would always recommend double checking your calculations. Make sure that you have calculated this data correctly, but it's 216. So now it says, to test the strength of the relationship between these two variables, the student decided to apply a Spearman's rank correlation test. Calculate the Spearman rank correlation coefficient for these two variables. So do not just plug all these numbers into your calculator. This is where it will go wrong. Okay, so mark it out, write it out step by step. So our value of Spearman's rank correlation coefficient is going to equal 1 minus 6 times, now we've worked this out to be 216. Okay, and we're going to divide that by our numbers of pairs of data, which was 9, multiplied by, again, our n value, 9 squared minus 1. Okay, next step, RS equals 1 minus 6 times 216 divided by 9 times, or 9 squared is 81 minus 1. Okay, next step, 1 minus, I might do my 6 times 216, which comes out to be 1296, divided by 9 times 80, which equals 1 minus 1296 divided by 720. Okay, so that equals 1 minus, let me grab my calculator, sorry. Okay, so we're over here now. Let's get rid of that. Alright, so 1296 divided by 720 equals 1.8. So our 1 minus 1.8 equals minus 0.8. So our answer is 0.8 minus. Okay, so remember what I said about the minus signs. So a student formed a hypothesis that the size of the limpets would decrease as the distance up the shore increased. Now this is slightly different from what we've been doing. This is an actual hypothesis, not a null hypothesis. So we have to look at the statistical data slightly differently. Critical values at different significant levels. Always the 5% significant value. Remember what I said, we don't take one away for this one. We do for the t-test, we do something called chi-squared, which we'll do later, but for this it's just 9 pairs of data. So this is our critical value. Okay, so this is our critical value here. So use the calculated value of RS, remember, which is minus 0.8, and this table to comment on whether the student's hypothesis can be accepted. So can we accept the student hypothesis? Well, we've got a value of minus 0.8, so that tells us that if there is a correlation, this is a negative correlation. It is greater than our critical value, so yes, we are going to accept it. Okay, there is a significant negative correlation between the distance up the shore and the size of the limpet. Why do we know that? because our calculated value is larger than the critical value at the 5% significant level. Okay, so it is significant, it's greater than a critical value. There is a correlation, it's a negative correlation. The further up the beach you go, the smaller the limpets get. Okay, so now we've had a look at that question, I would like you to have a go at this question, which is attached on Show My Homework, for another example of how to calculate the Spearman's rank correlation coefficient.